Hello again, gentlemen. This will be a re-upload of my previous video on enumeration. I've tried to do a bit of work on my audio and get a quieter keyboard, so hopefully this will be much better. So we were in the middle of this chapter by Dijkstra on our mental aids, and we've gotten to the section on enumeration. So in watching this video, what you're going to get is a look at the first kind of technique which Dijkstra points to that we can use to understand our programs. So Dijkstra begins, I regard as an appeal to enumeration the effort to verify a property of the computations that can be invoked by an enumerated set of statements performed in sequence, including conditional clauses distinguishing between two or more cases. Let me give a simple example of what I call enumerative reasoning. It is asked to establish that the successive execution of the following two statements, and you have them here, d is equal to d over 2, or is assigned to, and then if dd is less than or equal to r, do r is assigned to r minus dd. So you'll notice here that Dijkstra is using a kind of algo-like syntax that he won't really define. And I think it can be helpful here to try and translate this into a C-like syntax, though we won't be very strict in what we're doing. So let's just write this out as it would appear in a C-like language. We would say dd equals dd over 2, or if you like, dd is divided by 2. Choice is yours, but I prefer this form more because it's just more terse. So he's assuming he has an integer in context dd and another one r, but these are probably coming like we're within a function, and these have predefined values and so forth. So these are just think of them like they're in scope. And then the second statement is just a straightforward if condition. If dd is less than or equal to r, then we do r is assigned to r minus dd, which in C-like syntaxes, we write r minus equals dd. So this is the code that Dijkstra has over here. And now what is he saying? He's saying it is asked to establish that the successive execution of the following two statements operating on the values r and dd leaves the relations 0 is less than or equal to r is less than dd invariant. Now this is the important thing to understand. So what Dijkstra means, an invariant is something which, if you execute a block of code, an invariant is always defined relative to a given block of code. The idea is if the statement is initially true, so this is, you have a proposition here. So the proposition in this case would be that we have, let me just write it like this with a turnstile. And you'll notice I have ligatures enabled. So this is the pipe symbol followed by a minus, but I just mean it is the case that, so that's all that this symbol means. So it is the case that, assuming it is the case that 0 is less than or equal to r is less than dd, okay? The claim is that after you execute this block of code, that you will have the same property will still be true at the end of this. So basically what Dijkstra is saying is what he's going to embark on is an argument to show that if you begin with these statements, this statement here established, if you know this is the case, and then you do these two operations, at the end, you can be just as confident that this is the case. So he says one just follows the little piece of program, assuming that 1, and 1 is our formula over here. So this is formula 1. This is the proposition. One just follows the little piece of program, assuming that 1 is satisfied to start with. After the execution of the first statement, so now we've begun following it. So let's assume that this is satisfied. After the execution of the first statement, which halves the value of dd but leaves r unchanged, the relations 0 is less than or equal to r is less than 2 times dd will hold. So what is Dijkstra saying? He's saying if you know that focusing first and foremost on this side, but basically the other half also follows. If you know that R is in between 0 and DD, with this strict here and this not strict here, but if you know R is between them, if you have the value of DD, then now what applied to the previous value of DD will apply to 2 times that value of DD. This is pretty straightforward, isn't it? So now we can establish that at this point, whatever DD is, we will have this established. It's worth asking, I guess, because we're trying to be careful here, whether this is a property of real numbers or it applies also to integer arithmetic. So let's just think about that. Does this apply if we're doing only integer arithmetic? Probably, let's do this. So pause the video, you think about it and draw a conclusion, and then I'm going to tell you what I think. But I'm also going to probably cut the video here so that I can think it through. Okay, so I hope you took the time to think this through. My answer is that this actually does not apply to integers. And when we want to show that a property doesn't apply, all we have to do is find one counterexample. So let's suppose that DD here is an odd number. So for example, let's suppose that DD is 5. So let's just suppose that DD was equal to 5 here and R was equal to, well, let's use double equals, and R is equal to 4. Then after we divide through, we'll have DD is equal to, since it's integer arithmetic, it'll be equal to 2, and R will be equal to 2. Sorry, will still be equal to 4, right? And that means that you actually have DD, you have R is less than or equal to DD times 2, or 2 times DD. Okay? So what does this tell us? It tells us that as we're following this argument of Dijkstra's, it's wrong to think of DD and R as real numbers. We have to think of them, it's wrong to think of them as integers, and it's wrong to think of this operation here as integer division. This is more, so we just think of this as an exercise where we're trying to learn how to think about code, and I think we should just treat these as real numbers. Now, of course, if you're using floats or doubles, provided we're not in a case where floating point imprecision gets in the way. So provided we don't have an extremely precise value here, we'll be okay if we think of these as doubles, because we'll get, 2.5, and then 2.5 times 2 will be bigger than 2. But we just have to keep in mind that it could even be more complicated than that. So these are basically real numbers, or if you will, even rational numbers. And we're reasoning not in a, so let's just not think of these as regular programming operations, but let's think of these as, this is just an abstract mathematical example to help us reason through how we would approach something like this, but in a more strict context, or in a more, if you're reasoning about your code, you can't make this assumption here. So Dijkstra is just introducing this at a level that is, pedestrian. So let's just think of these as formulas in the regular mathematical sense. So these are real numbers. So now, assuming that these are real numbers, after you do this division, you will have this holding, right? So this is formula number 2, and he's saying that after you have DD, you're gonna have this will be now established. So now we come to Dijkstra's case analysis. So at this point, after we've done this halving and we've established this formula here, there are actually 2 possibilities. There's a possibility we enter the if condition, and there's a possibility we don't enter the if condition. So Dijkstra is saying we should think through them as 2 separate cases. So in the instance that at this point this if condition will be triggered, then together with this formula above, this formula 2, right? This leads to the relations that, DD is less than or equal to R, and we also have R is less than 2 times DD. So inside this if condition, let's say inside here, we can write another turnstile over here, and say that 0 is less than or equal to r, which is less than 2 times dd. This is formula 3, or proposition 3. And this is just taking the top half over here and this condition over here, right? So we're just joining these two. Oh, I beg your pardon. This should say dd. So if we're joining these two, so we've entered the if condition, therefore dd must be less than or equal to r. And then on the upper half, we have r less than 2 times dd. In this case, Dijkstra says, the following do will be executed, i.e. we will be inside the if condition, ordering a decrease of r by dd, so that from 3 it follows that eventually, that is after this statement, now we're going to subtract dd from r. And because this is true, this formula is true, we will end up with r equaling r minus dd, right? So for the new value of r, it is as if we take the turnstile and we subtract dd from every part of the proposition here. So if we subtract dd from the first one, we're going to get a 0. If we subtract dd from, let me just space this. If we subtract dd from here, we're going to get r minus dd, but this is our new name for r, so we're going to get r here. And then 2 minus dd is going to be equal to dd. And lo and behold, this is formula 1 again, right? So notice that passing through the if condition, we come out at the other end with our original predicate on our values established again. Okay, so that tells us that 1 will be satisfied if we enter the if condition. Now we consider if we don't enter the if condition, none dd less than or equal to r, the invalidation case. So we get to this point, but we don't enter the if condition. So what does that mean? So essentially, if we're in this else case, of course we won't write the else ordinarily, but we're just trying to reason through this. What do we know? We know that he calls it none dd is less than or equal to r, but we can also write this in the C tradition as not dd is less than or equal to r, right? Which is the same thing as, which implies or is equivalent to r, dd is strictly greater than r, right? So in this case, the statement following do will be skipped, and therefore also r has its final value. In this case, the dd strictly greater than r together with 2. So now he's saying we come back to 2 and we take this formula. This 2, the lower half tells us that 0 is less than or equal to r is already true. And here we've already established that dd is strictly greater than r, which is another way of saying that r is strictly less than dd. So we have both parts of 1 satisfied again, and you can see then that will come out with our formula still as true as it was when we began. And so thus we have in both cases the fact that at the end of the execution of these lines of code, we're going to have 0 is less than or equal to r is less than dd. Thus we have completed our proof of the invariance of relations 1 of 0 is less than or equal to r is less than dd. We have also completed our example of enumerative reasoning, conditional clauses included. So I hope that's clear, guys. And then next time we're going to look at the section on mathematical induction, which is a far more powerful tool and is necessary for dealing with loops, recursions, and the kinds of things that we use in real programming.